Very good morning, good afternoon, good evening all my students, and welcome back to this TQM2 course under the NPTEL MOOC series, and this is the 34th lecture, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember, we were discussing different designs, fractional factorial models depending on the number of variables and attributes which are there, number of levels of significance they are. That means you are trying to find out 3 to the power 3, 3 to the power 4 or 4 to the power 5. Technically it would be n to the power k, and technically n would be the number of levels of differences which you have for each factors, and there are k number of factors, and there are obviously different concepts of trying to find out the blocks according to which the design can be made, then the folding concept, then trying to basically subsume the relationship with higher orders. So, we can find out the maximum amount of variation, and as you remember, the main emphasis would be on the table which consists of the different variables, their sum of the squares of errors, then the degrees of freedom, the f statistic, the p value based on which you will comment. The 3k factorial design of the 3p blocks. So, here p is less than k, and you will do your block design depending on the variables accordingly, such that you have the minimum number of blocks to do the maximum amount of such predictions, or trying to find out the ANOVA output to the maximum possible level. The 3k factorial design may be confounded in a 3p blocks of 3k minus p observations. So, you want to basically partition in 3 to the power p blocks, and the partitions of the observations would be done accordingly. And if you remember that for the last example in the last class, which was in the 33rd class, we did mention that how the number of observations in each block were exactly 9, and you had 9 blocks. So, obviously, those things should be remembered accordingly. So, 9 was a number specific to the example, but obviously we will design it such that the equal number of variables are there. The 3 to the power k factorial design may be confounded in 3p blocks of 3k minus p observations each, where p is less than k. The procedure is to select p independently effects to be confounded with the blocks and find out their effects accordingly. As a result, so technically you will basically have effects which are automatically confounded would be given by 3 to the power p minus 2p. So, 3 to the power p blocks are there, and you are trying to, and minus 1 would be basically for the loss of degrees of freedom, and the total combination which you are doing would be 3 to the power p minus 2p minus 1 and divided by 2. So, that would be the total other effects which are automatically confounded. These effects are the generalized interaction of those effects originally chosen. So, let us consider an example with 7 designs to be confounded in 27 blocks. So, 27 would be 3 to the power 3, 3 into 3 into 3, 9, 9 into 3, 27. So, obviously, total number of variables is 7, and blocks would be basically designed 3 to the power 3. Because p, so obviously k is 7, p is 3. Because p is 3, we should select 3 independent components of the interaction automatically confounded. So, the others one which would be confounded would be 3 to the power 3 minus the same formula 2p. So, 2 into p is basically 2 into 3 minus 1 divided by 2 would be give you 10. So, the total number of 10 confounded automatically. And suppose, consider hypothetically we choose them as the blocks as a b c square d g or b c e square f square g, and so on and so forth. So, 3 defining contrasts can be constructed from these effects, and the 27 blocks can be generated by the methods previously described, and we can do the partitioning likewise. The other 10 effects confounded with blocks are mentioned in the next slide, and we will see that how it can be done for this example, where there are 7 variables and number of such blocks should be designed is 27. So, p is basically 3. So, if we consider the blocking, so you would basically have the blockings as given, as I will just mention one of them is a b c squared into d g. So, obviously, the blocking had been done where the effects of few of them would be considered at a higher level or lower level depending on the levels at which they are interacting each other. So, it is a b c square d g into b c e square f square g, and if you continue accordingly do the calculations, it comes out to be a b square. So, a d are at order 1, b e f g are order 2 depending on the level of significance. So, if you consider accordingly, you would have, I am just using the last one. So, it would be a b e f g. So, this is a huge design problem which is about 3 to the power 7, which basically is 2187 observations. They should be arranged in 24 blocks of 81 observation each. So, basically you will have 81 observations in block 1, block 2, block 3, so on and so forth, or such 27 blocks. So, as the total number of observation which you have is basically 3 to the power 7, which is 2187. So, what you are doing, you are partitioning them into blocks such that the effect of each block, considering the number of observations which are there, which is 81 in number in each block, would give you the maximum amount of effect which you would be discernible. The fractional replication of the 3k factorial design and the 1/3 fraction of the 3k factorial design of the blocks. The largest fraction of the 3k design is a 1/3 fraction containing 3 to the power k minus 1, because that is a degree of freedom concept. Consequently, we refer to this as a 3k to the power minus 1 fractional factorial design. To construct a 3 to the power k minus 1 fractional factorial design, select 2 degrees of freedom component of interaction. So, obviously, that would generally be the highest order interaction which you are planning, and partition the full 3k design in 3 blocks. So, basically, and obviously, you should remember that in each block the number of observations should be the same. Each of these 3 resulting blocks is a 3k to the power k minus 1 fractional design, and any one block may be selected for use, and correspondingly the calculations can be done. Now, if you have, say for example, the component of interactions as a b to the power alpha 2. So, obviously, that power would which is 2, 3, 4 depending on the level of significance, technically that variable would have. Now, I am using the word level of significance in a very English form of sense, which would basically give you the level of effect these variables have on the total ANOVA output. So, if a b to the power alpha 2 to c to the power alpha 3, obviously a to the power is 1 where alpha 1 is 1, and the last one is k to the power alpha k is the component of interaction, and using the block we define, using this we define the block. So, then obviously the indicator such, I will not use the word variable, the indicator factor would be given as a b to the power alpha 2, c to the power alpha 3 till k to the power alpha k, and it is called the defining relationship of the fractional factorial design. So, each main effect or component of interaction estimated from the 3 to the power k minus 1 design has 2 aliases, which may be found by multiplying the effect of both I square in the mod 3 model. So, obviously, why mod 3? Because you are trying to find out 3 to the power k factorial. If it is 5 to the power k factorial, it will basically modulus on mod 5, and accordingly the calculations can be done. Consider 1/3 fraction of the 3 to the power 3 design. We may select any component of ABC interaction to construct the design. That would basically given by ABC, AB square C, ABC square, or AB square C square. Based on that, we can do the calculation. Thus, there are actually 12 different 1/3 fractions of the 3 to the power 3 design defined by. So, you will basically have x1. So, obviously, a factor is alpha 1, but we will considering as 1. Then x2 multiplied by its corresponding factor alpha 2 plus x3 multiplied by its corresponding factor alpha 3. So, obviously, alpha 1, alpha 2, alpha 3 can take any values. Here in this case, alpha 1 is 1, which is a mod 3, where alpha 1 is equal to alpha is equal to 1 or 2, and the u values or the modulus for 3 result of these combinations can be 0, 1, 2. Suppose we select the component of a b square c square, each fraction of the resulting 3 to the power 3 minus 1 design will contain 9 treatment combination, thus must satisfy the equation x1 plus 2x2 plus 2x3 is equal to u, and that is at the mod 3 level. So, you had basically 3 blocks, Each blocks, if you remember that they have the number of variables in each would be, one would be 0 0 0, which is at the lowest level for ABC, that is low low low. Then you have 0 1 2, 1 0 1, 2 0 2, 2 0 2 1, 1 1 0, 1 2 2, 2 1 1 and 2 2 0. So, 2 2 0, obviously I am only mentioning the first and the last one. The 2 2 0 means A as the highest level, that means there are 3 levels 0 1 2, A at the highest level, B at the highest level, C as the lowest level, which is 0. Similarly, you have design where U is equal to 1 for block 2. So, that starts from 100 and goes to 0 to 0. The block 3, which is for U 2, starts from 200 and ends at 120, and you can find out the levels. So, if you again take the same, I am repeating it, please forgive me if you are considering along my right arm the axis A as shown in this slide, and axis C, C means for C only, axis A means for A, is along the left arm vertical up, and the arrow going towards you basically is for factor C, for factor B, which is the y axis. So, if you basically find it and plot the points, so that will give you, and this is important things to note. So, if for U is equal to 0, U is equal to 1 and U is equal to 2, you have the so called cuboids, which will give you the corner points which are significant to that block only, which means that that combination of those 3 blocks in the directions as mentioned by the corner points would give you the best effect, or the considering that error would be minimized to the maximum possible extent. If any one of the 3 to the power 3 minus 1 designs is run, the resulting allied structure would be like this. You will basically have, I am only reading the right hand column, would be ABC, BC, AC square, ABC square, AB square, AB square C, AC and BC square. Based on that, you can find out the combinations of blocks accordingly. Consequently, the 4 effects that are actually estimated from the 8 degrees of freedoms on the design are A plus B plus ABC, B plus AC square plus ABC square. The third one is C plus AB square plus AB square C, and the last one is AB plus AC plus BC square. Based on that, you can do the calculations. This design would be of practical value only if the interactions were very small relative to the main effects, and we can find out the effects accordingly. Because the main effects are analyzed with 2 factor interaction, this is a resolution of 3rd degree. That means, we are trying to find out the effects onto the 3rd level such that it gives you the maximum contrast. Notice how complex the allied structures are in this design. Each main effect is allied with a component of interaction. If, for example, the 2 factor interaction BC is large, they will potentially distort the estimate of the main effect of A and make the effect corresponding to AB plus AC plus BC square very difficult to interpret. So, you are basically placing all your bet on one and trying to minimize the effects of the combination of that, which should not be, because if you want to find out the effect, it should be partitioned in such a way the effects comes out actually. So, consider you have 100 rupees and you want to basically apportion them into 2 investment and get the maximum benefit. So, the apportions can be done accordingly, the returns can be found accordingly, but if say for example, the variances are too high, and then obviously you will face a risk or a loss. So, you want to basically minimize that corresponding to the fact that the apportion of your effects are such that you get the best output considering the ANOVA model, whatever you are trying to predict. So, let us consider the design for U is equal to 0. So, if you let A denote the row and B denote the column, then the design can be written as follows. So, you have basically 0 0 0 where they are at the lowest effect, then 0 1 2 which is A low, B middle or average, and C is high level. 0 2 1 is, I will just repeat it, it is low, high, medium, that is corresponding to A, B, C. Then 1 0 1, 1 1 0, 1 2 2, 2 0 2, 2 1 1 and 2 2 0. The assumptions of negligible interactions required for unique interpretation of the design is parallel in the Latin square design structure which we have done. However, the 2 design arises from 2 different motives. One is a consequence of the factorial replication and the other from the randomization restriction with a 3 square 3 Latin structure. The assumption of a negligible interaction is required for a unique interpretation of 3 to the power 3 minus 1 of the third design concept, which is a parallel to the Latin square. If you remember, in the Latin square you were the 3 cross 3 square and it was replicated accordingly. However, the two designs arise from different motives. One is consequence of the fractional replication, another from the randomization restriction which has been put to the problem. The treatment combination in a 3 to the power k minus 1 design with a defining relationship is, so basically the indicator variable or the indicator function is again a to the power 1, b to the power alpha 2, c to the power alpha 3 till the case of k to the power alpha k. So, they can be constructed using a method similar to that employed in 2 to the power k minus b series, and the work can be done accordingly. First, we write down 3 to the power k minus 1 runs for a full 3 level factorial design in a k minus factors with the usual 0, 1, 2 notations as should be. So, the 0, 1, 2 notations are basically the level of interaction each variable has, that is medium, low, medium, high. This is the basic design in the terminology. Then so we introduce the kth factor by equating it to the variables or levels xk to the appropriate component of the highest order. So, based on that we have the equation is like this. So, we want to find out the effect. So, in one orthogonal direction, if you remember, we have mentioned that one was L1, it is not the norm, not the L1 norm, L1 or L2, and again L2 is not the norm for the Cartesian coordinate. So, L1 was basically given by alpha 1 x1 plus alpha 2 x2 plus till the case of alpha k xk, and similarly L2 would be given by beta 1 y1 plus beta 2 y2 plus till the case of beta L yl. So, L and k are not the same because the level of significance based on which you are trying to do the calculations would be different for the two different combinations of orthogonal sets. Consider it as in a very simple terms orthogonal sets, so that we are able to predict it maximum. So, in this case we have xk is equal to beta 1 x1 plus beta 2 x2 plus beta k minus 1 x to the power k minus 1. So, from this we find out beta I, and which would of the mod level 3, and this yields a design of the highest possibility resolution, so that we are able to predict to the maximum possible extent. As an illustration, we use this method to generate the 3 to the power 4 minus 1 fourth design with the defining relationship as the indicator function as a b square c d. It is easy to verify that the first 3 digits of each treatment combination in this table are 27 runs of the full 3 to the power 3 design problem. Based on the, so based on that we are trying to get the maximum throughput in order to help us in predict us at the highest level. This is the basic design. For a b square c d we have accordingly as obviously alpha 1 a to the power is basically alpha 1. So, alpha 1 would be 1, then c is to the power alpha 3. So, alpha 3 is 1, d is to the power alpha 4. So, alpha 4 is 1, and b is basically to the power alpha 2, where alpha 2 is 2. This implies that we want to find out that beta 1 is given by 2 alpha 1, similarly at the modulus 3 level, and based on that we can calculate. So, thus the equation comes out to be x4 into 2x1 plus x2 plus 2x3, and once we design the overall design levels. So, on the leftmost column if you see you have the values, it is basically A, B, C, D. So, obviously, the combinations would be what one extreme 0, 0, 0, 0, that is low, 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 and the other case it would be 2, 2, 2, 2, which is high, 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 high for A, B, C, D. So, if you see it, the combinations for design for the indicator A, B square C, D are coming out to be as given. So, it starts from 0, 0, 0, and it goes to the highest level of 2, 1, 2, 0. So, combinations would be found accordingly, and we can do the predictions likewise. The resulting 3 to the power 4 minus 1 fourth level design has 26 degrees of freedom that may be used to compute the sum of the squares for the 13 main effects which you are trying to find out. of the interaction. The aliases of each fx are found in the usual manner. For example, the aliases of a are given as a into a b square c d, which is basically found out accordingly, and for a into a b square c d whole square would coming out to be b c square d square. One may verify that the 4 main effects are clear of any two factor interaction component, but that some two factor interaction components are aliased with each other. Once again, we notice the complexity of aliased structures such that if any two factor interactions are large, it will be likely to be very difficult to isolate them with this design and do the calculations accordingly. So, other 3 to the power k minus p fractional factorial designs are for moderate to large values of k. Even further fractionalizations or fractionations of the 3k designs is potentially desirable. In general, we may construct a power of 1/3 to the power p factors 3 to the power k designs for p less than k and do it accordingly. The procedure for constructing the 3k to the power minus p factorial fractions is designed to select p components of the interaction level and use these fx to partition the 3k into blocks such that the fx comes out to be the maximum. The defining relationship of the indicator effect of any fraction consists of p fx initially is chosen in such a way. So, you had basically 3 to the power p to minus 2p minus 1, that whole thing divided by 2. So, you can find out how many blocks and how many such variables are there, such that number of blocks multiplied by the variables in each number of variables in each block would give you the total number of such observations which you have. We may also generate the runs defining 3 to the power k minus p fractional factors by first writing down the treatment combinations of a full 3 to the power k minus p fractional design and do the work accordingly. We illustrate the procedure by constructing a 3 to the power 4 minus 2 design, that is 1/9 from the fraction of the 3 to the power 4 design. So, let us see that a b square c and b c d b are the two components of the interaction chosen to construct the design. These generalized interactions are accordingly found out as a c square d and a b d square. So, if you remember here, alpha 1 is 1 in the first case, alpha 2 is not there because b is not there, which is 0, alpha 3 would be 2 and alpha in the second case it would be alpha 1 is 1, alpha 2 is 1, alpha 3 is 0, alpha 4 is 2. So, based on that you can find out what are the best combinations. Thus, the defining relationship of the design would be found out such that it will be equal to, I am reading the last one only, it will be a b d square, which is alpha 1 1, alpha 2 2, alpha 3 0, alpha 4 2. By writing the design of the resolution, the 9 treatment combinations in the design are found by writing down a 3 square design in the factors a and b, and those factors are given as x3 is equal to 2x1 plus x2 and x4 is equal to 2x2 plus x3. This is equivalent to using the AB square C and BCD in partition to the full 3/4 design into 9 blocks and then selecting one of these 3 blocks as the design factors. The complete design is shown in this figure. So, they are basically, we start at level of 0 0 0 0, that means all at the low level, and go up till, I am not reading the whole sequence, the last one would be 2 2 0 1, which is A B at the highest level, C at the lowest level and D at the medium level, average level. This design would basically have 8 degrees of freedom that may be used to estimate 4 main effects which are there. So, you are basically dividing them into blocks and multiplying the blocks in their with respect to their number of observations, such that we will get the aliases to the maximum level. The aliases of any effect can be found out by multiplying the effect of the modulus 3. The complete alias structure for the design is given in table 9.8. From the alias structure, so we can find out, we see that design is useful only in the absence of interactions. So, if there are interactions are there or not there, that will also have an effect. Furthermore, if A denotes the row and B denotes the column, then for the examining from this table, we see that we have basically the 3 to the power 4 minus 2 design of third design, and they would be of the Greco-Latin square. So, the square would be found according to the concept of a Latin square from the concept of mathematics of which is Greco-Latin square, and the combinations of how you are partitioning in the blocks would exactly be the same way how you have basically made them into the square. So, that will give you the maximum effect. Factorial with mixed levels, factors are 2 and 3 levels, you will find it accordingly. So, consider a design that has some factors at 2 levels and some factors at 3 levels. Due to some constraints, we are considering fractional factorial design. If all of the factors are quantitative, mixed level fractions are usually poor alternatives to a 2 to the power k minus p fractional factorial with center points. Usually, when these designs are considered, the experiment has a mix of qualitative and quantitative factors, with the qualitative factors taking on 3 levels, and or correspondingly the quantitative values should also be determined accordingly. The complex aliases we observed in the 3 k minus p design with qualitative factors carries over a great extent in the mixed level fractional system which you are designing. Thus, mixed level fractional design with all qualitative factors or a mix of qualitative and quantitative factors should be used very carefully in order to find out the overall effect. Suppose we have two variables with a at 2 level and x at 3 levels. So, we consider a table of plus and minus signs for the usual 8 run 2 to the power 3 design. The sign in the columns B and C have the pattern shown on the left side of the table, and which is basically 2 factor levels. It will be B at minus level, C at minus level. Other combinations are B at high, C at low, and another could be at B at low, C at high. Another combination would be both of them at the high level. The effect of the effect would be coming out in x1, x2, x3, x4. So, obviously, it will increase depending on more numbers of such B, C, D, and combinations levels also being plus minus or plus 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 0 minus minus minus, so on and so forth. Let the levels of x be represented as I said the x1, x2, x3, x4. The right side shows that the sign patterns of B and C are combined to form the levels of this 3 level factor model. Now, factor x has 2 degrees of freedom, and if the factor is quantitative, it can be partitioned into a linear and quadratic component, each component having 1 degrees of freedom, and calculations can be done accordingly. Table the next table, basically the side slide would show basically the 2 to the power 3 designs with the columns labeled to show the actual effects. Note that the level of effects of x is the sum of 2 effects estimate computed from the column. Similarly, you will basically have a to the power xl, a to the power xm, a to the xn, based on which you will basically find other combinations. I will come to that later on. So, similarly for runs of flow, 4 replications, 6 replications, 8 replications can be done, and we can find out the partitions accordingly to the aliases, to the folds, to the level of factors, to how many such blocks would be there, what is the number of such observation in each block. We will study it more details later on. Have a nice day, and with this I will end this lecture. Thank you very much.